So the hope is next Tuesday to at least have some robots that we can bring into class. I'll kind of go over what the robots are and also have Lab 5 ready for you then. So if some of you are still working on Lab 4, you can do that. Some of you want to start looking at the robots and see what they're capable of, and what, basically Lab 5 is exploring the basics of the robot. And so hoping to do that on Tuesday and then bring the robots in again on Friday, so then you have time to work on the lab, which is focused on using the robots. So of course they're over in JEC. So if anybody has a little bit of time before class on Tuesday or Friday to help transport them over, that'd be greatly appreciated. The alternative is I bring over one container and then go back and bring over another container, which not ideal. So if somebody has some extra time that can help with that, that would be great. Also, these robots do have lithium ion battery packs. And so there's safety considerations as part of that. So on Gradescope, there is it's like a Lab 5 agreement. So you should do that by the end of day Monday. So we have that in before you start working with the robots. That says basic things like if you're charging the robot, somebody has to be present in the room. Or you may have heard lithium ion batteries, they can explode, they can catch fire, things like that. So for safety concerns, somebody needs to be present. If at any point there are robots that lose their charge, but you can't be around to recharge them, let me know so that I can take some to my office if need be to try and keep them charged up so you have them when you want to use them. So ideally, we're going to get some more time in the shared space as well. So I'll be able to open up the space and you'll be able to work in there on the robots. And ideally, if you're working with one robot, you should be charging another robot. So that just keeps them all available. So whenever somebody goes in to use the space, it's charged up and ready to go. So take a look at that as information, and also be creating some kind of Google form so we can share when the last time was that robots were used or charged, so you have some idea of which ones are the best to work with at that time that you're in the space. Okay. I know I'm a little late on Lab 3. It's been quite a week, so I'm hoping next week to get those graded and back to you. My apologies for the delay. But if you have any concerns, let me know. Also, somebody did point out with one of the quiz questions that maybe the wording, the way it was presented, wasn't that great, and they had a little bit of confusion. If you come across any questions that are like that, please let me know so I can reevaluate and modify for next delivery if things are maybe not quite presented in a way that makes it clear what it is that I'm asking for, because I always know what I'm asking for. So, all right. So for today, what we're looking at is a very powerful package, which is the TF2 package. Those of you who took Robotics 1, don't get into too much of a panic, but it is those coordinate frames and transforms. Okay, so it turns out that when you're working with robots, right, you have lots of sensors, you have multiple robots, they're all working in a space. And so how do you actually tell where is something relative? Maybe I can measure where something is relative to my camera. How do I know where it is relative to my robot, where it is relative to the world? How do I know where each robot is relative to each other? And the way that we do this is by assigning coordinate frames to all of the things that we're interested in. So I installed, and if you look at the slides, you'll see more detailed instructions. So there's an example which utilizes the Turtle Sim to explore this TF2 package. And let me get my cheat sheet here just in case. So this initial demonstration, they have a launch file. And so if we run that, right, control paste. and our first terminal. So what this is doing is it's creating one turtle, and then it creates another turtle, and you can see that the second turtle moved automatically. Okay. Now if I open another terminal and I do a ROS to run of the turtle sim, and I do the turtle teleop. Okay. So you notice I'm moving one turtle and the other turtle is following that, right? So the way that it's able to do that is it's able to actually recognize the coordinate frames, and it's able to tell where do I need to move turtle 2 to make it match the pose of turtle 1. Okay, so really powerful thing that's going on here. And so one thing that you can do also is you can visualize the frames that are associated. So if I do a ROS2 run TF2 tools, the one thing is that this is going to, similar to those parameter dump files, right? It's going to create a PDF file in whatever your working directory is. So I just went to the desktop so it's easier for me to find. And so what it's going to do is it's actually going to listen, see what all of the TF transforms are that are being published at that time. And then if I go to my desktop, right, so there's this frames.pdf, and why is it? That's going to be difficult. Right, so there we go. Right, so now you can see that what this TF tool does is it generates a tree for you. Right, so what we can see here is that we have two frames, turtle 1 and turtle 2, which are both tied to a parent frame, which is world. Right, so it's able to know where turtle 1 is relative to this world frame, and we're able to know where turtle 2 is relative to this world frame. And based on that information, we can actually also compute where is turtle 2 relative to turtle 1. Okay, so those who took Robotics 1, right, you probably recognize that stuff that we talked about. Yes, it is useful and it does come up again. Right, so let's take and look at another tool that we have available. I'm going to detach this terminal. Right, so we also have in our ROS to run TF2 ROS, there's another tool called TF2 Echo. And so what you supply to this TF2 Echo, the first thing that you provide is your source frame. The second is a target frame. And so what we'll see is that it's going to print out some information. And what this information does is it tells you essentially how would you move the source frame to match the target frame. Right? So if I said the world is my source and turtle 1 is my target. So sometimes it takes a little bit of time for the frame to become available. So you can see that it's printing out a translation and a quaternion. So quaternions are a way that we can represent rotations, right? So translation is probably pretty straightforward. It's telling you how would you move in X and Y to get to the target position. Quaternion we'll talk about a little bit because that might not be as intuitive if you haven't seen it before. But if I take my turtle, and unfortunately with the scaling on here, it's not great to see. Why are you not working now? There we go. All right, so if I take my turtle all the way down to the bottom corner here, and I'm going to have it facing to the right. So now if I look at this here, right, we can see that it's telling me that my turtle 1 is essentially at the origin of my world frame, right? Because to get the world frame to the turtle frame, I don't have to move at all. And then we'll also take a look at what the quaternion here means in a little bit. But first we'll just take a look at the position here. So now if this turtle, I move it forward in the turtle frame, right? So we can see as moving along this bottom edge that the translation has increased in X, right? So we know that for this world frame then, this point at the bottom left corner is our origin. This direction is our X. And if I rotate to look upwards and I move up, you can see now my Y position is increasing, right? So I know that my world frame, I have X, Y, and if I haven't mentioned before, right-hand rule to figure out what the Z direction is. If I put my fingers in the direction of X and curl them in the direction of Y, where my thumb is pointing is where the Z axis is. So in this case, the Z axis is pointing out of the screen. And so if we look at our rotation, so I'm going to go back to my slides here. Okay. So what we're going to find is that for the turtle, and you might have noticed this before when you were looking at some of the other labs, this was asked. And it turns out that the X-axis is pointing out the front of the turtle, right? So it might be a little hard to see, but here's the legs of the green turtle. That was my turtle 1 at the time. So the X-axis, which is red, is pointing out, and then the Y-axis is pointing to the turtle's left. And so we can see here, right, so we would have a different coordinate frame associated with each turtle. And then we have a world coordinate frame, which is associated with the screen that they're operating on. And so to actually get to the quaternion, what that means for rotation, so you can clone from the RPI Robotics GitHub. There is a robotics toolbox that has been implemented in Python, and it has a lot of different functions that are available in there. And so I'm going to utilize these a little bit. But what you can do with this toolbox is you can convert the quaternion into Euler angles. So thinking in terms of rotation about X, Y, and Z axis. So that might be a little bit more intuitive to figure out like what is actually represented by the quaternion. What's nice with this example application is that everything is happening on a 2D plane, right? So the turtle can't rotate. If we look at our figure here, right? The turtle can't rotate about the X-axis, right? It can't rotate like this. It can't rotate about the Y. The only rotation it can actually do is around the Z-axis. Right? So that's why you might have noticed with some of the different twists that you only see X, Y translation and Z rotation, and that's because we're restricted to this plane. And so what'll happen when you're working with this specific example, since it's only 2D, what you can do is you can convert your quaternion. So this will explain in a little bit what R is. So R is a rotation matrix. So you can convert the quaternion to a rotation and then convert that to roll pitch yaw, where yaw is going to be a rotation around the z-axis. And so then it's going to return the rotation in radians. So you can convert that to degrees if that's more intuitive for you to recognize what that angle is. Okay, so those that take robotics 1, it took us a little bit of time to go through this. So if you have any confusion, if you haven't seen this before, we can go over a little bit more. It's definitely one of those things where rotations can take some time. Some people can visualize it very easily. Some of us are still sitting in our room doing this, trying to figure out what it actually is. Right? So the idea here is that there are different ways that you can represent rotations. Right? Because we had those coordinate frames, but we want to line up the coordinate frames, right? We have to rotate one or the other to get, say, the x-axis to align and the y-axis to align, and the z also in 3D. And so different ways that we can represent quaternion, Euler angles, and also rotation matrices. There are a few others as well, but these are the main ones. And so what the rotation matrix does is it allows us to map, if we have something in our target frame, to figure out what it would be equivalent to in the source frame. Okay, so I'll take one example here. So with this quaternion that I have provided, this would be the case where if, say, this source down here was your world, and this target was your turtle 1. Okay, so what this would represent is a 90-degree rotation about z. Right, so this rotation is essentially saying, how much do I rotate my source to match my target? And whether it's positive or negative depends on the direction that you're rotating. So for this, the z-axis is pointing out of the screen. So a positive rotation would be the direction that your fingers curl in. So to get the source to line up with the target, I need to do a rotation counterclockwise. So in this case, that would be a positive rotation, because it's a positive rotation around z. Okay. So I can do this conversion. I can figure out this quaternion here corresponds to a 90-degree rotation about z. And I can also convert this into a rotation matrix. And so this rotation matrix is for the 3D case, so it would represent full XYZ rotation. Since we're only working in a plane, what we can actually do is just take these top left 4 values and use that as our 2D equivalent. And so what we can see is that if I take this rotation matrix, and let's say I'm looking at the x-axis in the target, right? So I'm looking at this red line here. And the question is, what does that look like relative to this frame, right? So if I was to line up these origins, you can see that this red axis is pointing in the same direction as the green axis for the source. And so we can see that if we take our target representation, apply this rotation matrix, that what we do indeed get is that that's the equivalent to the y-axis in the source frame. Okay? We can do a similar thing if we look at the y-axis in the target. So the y-axis is this green, and we can see that it's pointing in the opposite direction of the x-axis of the source. So if I apply the rotation matrix here, we do indeed get that y-axis in the target looks like negative x in the source frame, right? So this one is not too hard to visualize. If you get, say, this is at some weird angle here, and you want to know, I see something in the turtle frame, where is it actually relative to the world frame? You can use this to figure that out. And it turns out with rotation that if you want to go in the opposite direction, right? I give you something in the source frame, and I want to figure out what does it look like in the target. All I have to do is do the inverse of that rotation, and it'll get me what I want in the other frame. Okay. So really powerful tools to be able to see where things are relative to each other. Robotics 1, we dig into that a lot more. For these purposes, we'll see that TF2 handles a lot of these transforms in the background for you. So if you're not 100% sure what's going on, it's okay. Come to Robotics 1 and figure out what is actually going on with those and what they mean. But this gives you a little bit of an idea of what that information is that is actually returning for you. Okay. So with the transforms package, we can implement different types of transforms. Okay, so the transforms are telling you that relative position and relative orientation between different frames. And so you could have multiple types of transforms. Right? So you could have a static transform. Okay, so maybe you have a camera which is mounted onto a mobile robot, and since that's rigidly mounted, whatever frame you assign to your robot versus whatever frame you assign to your camera, the transform between them, that relative position and orientation, is not going to change, right? Because the camera is always going to move with your robot, right? It could also be, say, if you have a robot arm and you stick that in your work cell, and so it's bolted down somewhere in the workspace, is not going to move, then that would be a fixed transform between that base and whatever frame you're using to represent your work cell. Versus something like a dynamic transform, right? So if you think about the end of the robot, so maybe your grippers that you have, that's going to be changing relative to the fixed point at the base of your arm, right? So there you have a dynamic transform, and because we know, so in Robotics 1, you would learn things like kinematics, where you can do the mapping and figure out if I know where this endpoint is, I can figure out where it is relative to my arm. So we can use these transforms to figure that out, right? So maybe when I'm controlling the robot, I tell it, here's where I want the end to be relative to my base. But maybe I have a camera which is on the end of the robot and it sees an object. And so the camera knows where the object is relative to the camera. I need to control to get to where the object is relative to my base, right? So you have a chain of transforms that need to go on in order to figure out where do I actually need to command it to go to. Okay. So with the static transforms, you can actually just publish these in the command line, or you could add them to your launch file. And so there is a built into TF2 ROS. There is an executable, which is the static transform publisher. And so you can just provide the arguments for it and say, I have some frame. So maybe this is my world frame, and I have a child frame, which might be the base of my robot. And then I tell it, okay, so the child frame relative to this frame is at this XYZ position and has this roll pitch yaw orientation, or you could also provide in quaternion form as well. And so this is a static transform. It's not going to change. And this publisher is going to handle the background of what actually needs to be done to add that to your transform tree. Okay. So it is also possible to add it within a script as well. So within, say, your Python file. That's usually not as recommended because if you have a static transform, it's not changing, so it kind of makes sense to put it in something like a launch file. But you can do that as well. So I'm going to go back to the lecture or the VM here. Okay. So what you can do with this, and I have the additional instructions on the slide is that you can create these broadcasters and let's close everything out here. Right, so you can have broadcasters and you can have listeners. Okay. So what your broadcasters are doing is they're actually sending out transform information, and then your listeners can listen to that information and act on it however they want to. Okay, so I created a new package here. Right, so we're testing the TF2 and Python. And so we have a turtle TF2 broadcaster here. So some of the main things that we notice here, right? So we have this from the geometry messages package, which we've used some things in there before. There is this transform stamp. So this is actually going to contain that XYZ roll pitch yaw information. And with a stamp, it's also going to contain a time index, right? Because it might be possible that as you're moving around the robot, maybe you're actually interested in what you got from maybe another robot some time ago, right? So maybe you want to go to where another robot was previously. So it's good to know when did you actually get this transform information, so then you can use that as well. Okay, so a lot of this looking pretty similar, right? So our RCLPY and node, we have this new thing coming from our TF2 ROS, which is our transform broadcaster. Okay? And so this transform broadcaster is going to implement everything that we need to know to actually create this transform. So there's some additional things going on here, right? So there's the math for converting quaternion to roll pitch yaw. And they have a parameter here, which allows you to specify the name of the turtle that you're interested in looking at. And it has a default value for that. And then as we keep going down here, right, so we initialize our transform broadcaster. And you can see here that we have a subscription that is looking for the pose of another turtle. Right? So essentially what this is doing is recreating the example that we saw, where you have one turtle that's following around another turtle. So when it gets a pose, it's going to call this handle turtle pose. And so we can see here is going to initialize this class type, which is the transform stamp, or this message type transform stamp. And then it's going to populate different fields within that. Right? So the stamp is telling it the time. And so this is actually taking from the clock, which is built into the node type, which comes from ROS. We're telling it, I want the time now. And then this converts it into the form that it needs to be able to actually implement it into the message type. And then you also have this frame ID. So this is specifying the source frame. And then this child frame is essentially the target frame that we're looking for, if we compare it to the terminology we used before. Right? And then it's actually getting, based off of the pose that it read, where the XY data is coming from. Right? So as I explained before, since everything is happening in a plane, then our Z translation is always going to be 0 because they can't move out of the screen. And then same thing with the Euler angles, that you're never going to have a rotation about X or Y. It's always going to be a pure Z rotation. Okay, so it populates that information, and then it's going to actually send out that transform, so then it's available for you to read with a listener. Okay. So with this, then you would go through the same kind of stuff, right? Modifying the package XML and the setup file as well, same way that we've seen before. A little bit different, we do have this, we've also imported NumPy in here, so it's also good to include that in your dependencies as well in your package XML file, right? Just to make sure that you have access to everything that you expect to have access to when you run this file. And so I also want to take a look at a launch file here. So the first one we want to take a look at is our TF2 demo launch. Right, so we can see what this is doing is it's going to have this node here, which is our turtle sim node, right? So it generates that first turtle. And then we have a broadcaster, right? So that's what we just looked at. That's going to make the information available. And you can see that that parameter that we had, which is looking for what turtle are we interested in, it's going to populate that with the turtle that we generate from that initial turtle sim. And then, if you recall, you can also have arguments that are available when you launch a file. Right, so these are additional parameters that you can provide after you do the ROS2 launch, whatever the file name is, then you can add some additional information. And so you can provide a different target frame. By default, it's going to be turtle1, right? But you can change it to something else. Right? And then it's actually going to create another broadcaster, which is going to be associated with turtle2, right? Because it's going to run 2 of those. And then it's also going to start a listener to look for that information. Okay. So as we already saw, because it's basically just recreating what we saw before, you can do the same thing that we did. So you have both terminals open. You can do the TF2 echo, and you'll see world versus turtle1, or you could do turtle2 versus turtle1 as well. The listener file here, we gotta go back. It's our turtle TF2 listener. Okay. So for this one, some key differences. Right, so we have a lot of things are similar, except we have this new thing, transform exception, and we also have this thing buffer. And instead of the transform broadcaster, we have this transform listener. Okay, so we go down here. All right, so we have a parameter like we've seen before. Here we go. So we can see here that we initialized a buffer. Right, so what this buffer does is it allows you to store up to, by default, 10 seconds of the published transform, right? So you can, as you're listening, you can keep a buffer of previous values. So then if you need to go back, or if there's maybe some communication issues in your channel, that gives you some data that you can work with, even if you don't have a reliable connection, right? So it provides that buffer for you. Okay. And so, all right, so this is using the spawn service that we looked at before. Publishers like we've seen before, right? So we can see what this is doing. Right, so there's a little bit more going on here because what it's trying to do is make sure that the spawn service is actually available, right? Because it's going to generate one turtle initially, and then it's going to spawn a second turtle so that you can follow the first turtle with the second turtle. So this additional information that's here, these nested if statements, are just checking to see, is the spawn service available? Has the turtle been spawned yet? If not, let's actually create that turtle. Okay. So one thing we haven't used this before, RCLPY time.time. So that is actually going to look at the current latest time. So this lookup transform here, what this is doing is it's going to look at based off of your 2 frame and your 4 frame, right? So your 2 frame would be your target and your from your source. And so you provide those two frames, and then you tell it, I want it at this current time. Right, so I'm going to take those two frames and compare them and see how would I have to move to actually get from this source frame that I provided to this target frame that I provided. Okay. And so that's kind of the key thing here for the listener, is being able to actually look up that transform and figure out where frames are relative to each other. And this also ties to the idea of the transform tree that we saw, right? If you have anything that's not connected, so say if I had a turtle 3 that was off to the side and I wanted to do turtle 3 versus world, if there's no connection between them, then this would actually fail. And so that's what this transform exception is in place to catch. Right? So the transform exception is going to check, it could be things like your, maybe a specific frame isn't available, maybe there's not a direct connection between them. This transform exception is going to catch all of those. And we'll take a look a little bit later about some of the additional transform exceptions that exist as well. Right, so a little bit more going on. Some of this you should be able to recognize from previous examples that we've looked at, how to use services, how to publish to different topics. So all of that is pretty similar to what we've seen before. Okay. So that kind of gives you an overview, and as I said in the slides, it walks you through how to actually recreate these files. And so these files here are going to replicate that initial example that I showed to you. And so what you can also do with your transform, right? So you can also add additional frames. Right? So we'll look at a couple of examples where we can add some other frame which are going to be relative to our turtle frames. Right? So we can actually cascade and have more children down the tree which are related to higher frames on that tree. And one thing is that you notice in the example that we looked at, I was always looking at the time right now. Okay? But you could actually say, actually, I want turtle 2 to go to wherever turtle 1 was 10 seconds ago, for example, right? So you can actually do that with the TF2 package as well, okay? So I also have walking through how to do some of these examples as well. But the first one, what it's going to do, it is going to add an additional fixed frame, so a static frame relative to my turtle, okay? And it's going to be relative to turtle 1, that first turtle that we broadcast. So if I open up my fixed frame broadcaster, okay, so a lot of things are going to be pretty similar to what we've seen before. Right, so we can see here, right, so we have our source frame is our turtle 1, and then we're going to create a new frame which is relative to this frame. Right, and so as in kind of sticking with the turtle theme, we're going to say that there's a caret that is relative to the turtle. And so what we're saying is that this caret is going to have the same orientation, right? So this is in terms of the quaternion. So with a quaternion, it's going to be a 4-value vector, which is x, y, z, and omega. So if you're not familiar with quaternions, like I said, that RPI Robotics toolbox is going to provide some functions that you can convert, say, roll, pitch, yaw, into a quaternion for you. Okay? And so this 0001 means that the orientations are going to be the same, right? So if the x of the turtle is facing forward, then the caret frame is going to have the same x-axis. And we're going to put this caret at +2 translation in the y. Right, so if you remember from our coordinate frames, out of the front of the turtle is X, to the left of the turtle is Y. And so essentially what we're saying is the caret is going to be 2 units to the left of the turtle. Okay? And so what that means is that when I go and actually test this functionality, okay, so make sure that I do my my source of my test workspace. Right, so I can do ROS2 launch. So there's an additional launch file that was created specifically for this fixed frame demo. And what I can provide as an additional argument for this launch file is a target frame. And I want my target to be the caret. Right, so this is going to look similar to what we saw previously, except now instead of following turtle 1, right, so what we're going to see is that turtle 2 went 2 to the left of turtle 1, right, because it's following the caret, which is relative to turtle 1, but it's actually following that instead of the turtle. So if I was to open up and do a ROS2 run of my turtle sim and a turtle teleop. So now if I move around my turtle, right, you can see that it's actually following where it's going to stay that 2 away. Right? So it's actually following that other frame. Okay. And so you could also have a dynamic frame instead of a static frame like what we have here. So take a look at that example. Right? So with this example, we go down to our broadcaster unit. Right? So you can see before what we had was we had a fixed position for the Y translation. Right? Instead, what we're doing here is we have here we're actually reading from the clock to figure out what is the current time. And then we're converting that into a value that we can feed into sine and cosine. Right? So what we'll see here is that the position of the caret is actually changing with time. Okay? So if we run this example instead, right, so we're going to have ROS2 launch instead of the fixed frame. We're going to do the dynamic frame. Okay. Right, so you can see that it turns out the caret is actually moving. So even though I haven't moved the turtle at all, like turtle 1, turtle 2 is trying to follow this mystery caret that's moving around based off the current time and those sines and cosines. Right, so interesting little demonstration, you know, maybe not as realistic as some, but you could relate this, say, if you were maybe trying to track, maybe you have something that's on like a conveyor belt and you're trying to track it with, say, your arm, right? So that's where you could have something like a dynamically changing frame that you're trying to interact with. Okay. So those are the two main types of frames, right? The static and the dynamic. Looks like our turtle has reached some kind of holding pattern at this point. But again, this is just using current time, right? So what if we actually want to utilize the time indexing, right? Because for all of these, we're using this time stamped transform. So we have this time information. And so let's see if we actually want to utilize this time, how we can do that. So as beautiful as it is to watch, I'm going to kill this. Right. So just so I had copies of everything that I had worked on, I put this into a separate package. And so I actually copied a lot of the files and then just tweaked them for the specifics, looking at the time indexing. Right. So if you look at the turtle listener, right? So right here, so here's another thing that we can add is that we can also add a timeout. Right? So what this timeout does is when you're looking up this transform, right, it'll actually wait for a certain amount of time to see whether or not the transforms are available. Right? So it's going to hang out there until it can see both the target and the source frame. And if it passes that certain amount of time, then you're going to get a timeout error, right? And so it's actually going to exit and give you that exception so you know something is wrong, something that should have been available is no longer available to you. Okay. And so these exceptions, and I'll actually jump over to my slide so we can take a look at these. Okay. So the transform exception that we saw in the first example, that's basically your umbrella term, right? It's going to catch any of the exceptions that could be raised by TF2. But it might be that you want maybe some more specific reactions depending on what exception that you have. Maybe there's certain ones that you don't really care what happens, or you know, want to handle them in some different ways. So there are actually a bunch of different exceptions that are under this transform exception umbrella. Right, so some of them might be fairly intuitive from the name, but I also tried to give some of the things that might cause this. So a lookup transform basically means it can't actually do this lookup. Right? So that could happen because maybe one of the frames is not available yet. Right? So maybe if you're trying to look up the transform between turtle 1 and turtle 2, but turtle 2 hasn't been spawned yet. Right? That would give you a lookup exception because it can't find that second turtle. This could also happen if when you're defining all of your frames, maybe you're missing a connection between them, right? So it could happen, maybe you have your world and you have turtle 1 and turtle 2 that's over here. Then you have a turtle 3, which is relative to maybe a platform which is in the world, but you never actually specify where is the platform relative to the world, right? So then you actually have a disconnection in your tree that the TF package can't figure out. It needs to have some way to trace through the tree to make that connection. So that's another way that you can get a lookup. Connectivity, right? So if you don't have a connection between those, extrapolation. So this is something that could actually happen if you accidentally request based off of information that you don't have yet. So it is possible to utilize your buffer and store up a bunch of information and then utilize that. It is possible that you accidentally put in some parameters where you're looking for something that's not available to you at this time. And so it can't actually extrapolate where you're going to be in the future, right? It only has the information up to a certain point. There's also an invalid argument exception, as that usually comes about if your quaternion definition isn't correct. And then the timeout exception, right? So we saw in the lookup transform, you can add a timeout time. And so if you exceed that time, it's going to give you a timeout exception. so you know that something went wrong there. So we go back to my file here. Right, so we can see that what we changed, instead of using all of the exceptions, we're just looking at some specific ones, and then we can provide some specific feedback based off of those exceptions. And so then, so if I want to based off of a previous time, so because I also kind of have this this modified based on the second step as well. So if you follow along with the slides, not all of this changes would be in place at this point. The next changes that we would make is if I want to move my turtle based off of where turtle 1 was previously. Okay, so what I can do here is I can define this when that I'm interested in is going to be, right, so the first part is saying what is the current time, and then the second part, so this is just making sure that everything is in the correct form so that you can actually do the subtraction, because they need to be the same type of data to be able to do that. And so we can use this time duration to actually get the number of seconds that we're interested in. And so we can separate this, and basically this is saying the when that we're interested in is 5 seconds before now. Okay. And so if you were to use what we had previously, and so instead of having this target time and source time, if you just had a target frame, source frame, and then you had the time as when, and you tried to run this, you would notice very terrible things that was going around, right? So why that is because if you only provide the time of 5 seconds ago, then what the turtle is trying to do is it's trying to go to where it should have went relative to where the carrot was and where it was 5 seconds ago, right? So if 5 seconds ago I needed to move my turtle forward 3, right? And I've already moved some, but it's still trying to move forward 3 because that's where it was before, right? So you have this inconsistency between what you want the program to do and what it's actually doing, right? So a lot of people, when they're first writing code, they say, well, it's not doing what I told it to do. Well, it turns out your code always does what you tell it to do. You're just not telling it what you think you're telling it. So what we really want this to do is I want to figure out where do I move my turtle based off of where I am now, based off of where the carrot was 5 seconds ago. So a way that we can clarify this is we can use, instead of lookup transform, there's this lookup transform full. So full allows us to provide some additional information to get more specific about what it is that we're looking for. And so the target frame, source frame is the same as what we had before. Now you notice that we have additional time as well. Right? So we can tell it for my target, I'm interested in where it is now. Right? So my target, if I look up there, the 2 frame is turtle 2. Right? So I'm interested in where the turtle is now. And then if I look at my source time, right? So the source time, I'm interested in the from frame, which is the carrot, where it was 5 seconds ago. That's what that when variable is telling us. Okay. So the one thing with this is that you need to have a reference frame for both of these, right? And it needs to be a fixed reference frame, because essentially what's happening in the background here when we provide this is that it's figuring out where was the source frame relative to the fixed frame at that previous time. And then it's figuring out where was the target relative to the world at the target time. And once it has both of those relative to the world, then it can figure out where the turtle needs to go to. Because it can actually do the mapping between the turtle and the carrot. But first it has to go through the fixed transform. And if you just have a bunch of moving frames, right, then you're not going to have a good reference for where each of those things are relative to each other now if it's based off of something that's moving. Right. So if that explanation is not clear, let me know. It gets a little fuzzy when you're dealing with coordinate frames and then you have times going on as well. So definitely as you're looking through this stuff, if you're kind of confused as to what's going on with it, please let me know and then we can take a slower look at that. Right, but if I look at the time case, right, so on this one, so I want to do my fixed frame demo, but I'm going to use my time change version. So in this case, if I move around turtle 1, right, so you notice that 5-second time delay. Right, so it's actually following where the turtle was 5 seconds. Well, the carrot was in this case because we do have that offset. It's going based off of where that was 5 seconds ago. So you can see the time delay that's happening as we move it around. Right, so an interesting and powerful tool definitely comes up a lot in robotics, right? So with things like mobile robots, you're going to have all of your sensors. You need to have some reference frame for the robot itself to figure out how do I actually need to move it? Where is it in my current space that I'm working in? With arms, you would have same kind of thing where you're interacting with your environment. So you have coordinate frames associated with objects. You have coordinate frames associated with different parts of your robot, any sensors that you have in your workspace. And so it can definitely get overwhelming if you're just looking at it mathematically. But this TF package allows you to have all of this handled in the background. Right? So you can have 100 different frames and you can use the lookup transform and say, all right, how do I move this thing to get it to match up with this thing? Where is it in relation? And as long as everything is connected within your reference tree, it's able to do that calculation for you. Right? And so those in robotics 1, you learned what that math is that's actually doing to get all of that information. But that's basically what's happening in the background of this TF2 package. So I may went a little fast today for some reason. Are there any questions about any of that? Yeah. So I know there is a PID in the background that is tracking the position, and it could be just a little bit of noise in what it's reading. So it could be just that it's over responding to that little bit of noise in the orientation that it's reading. I'd have to dig in a little bit more to give you a more concrete answer, but there is a background PID that it's using. And you can tell if there's a PID because you can see that it's kind of doing this correctly. It's not exactly following the position, kind of tracking close to that position. All right, so I'll give you some time to take a look at Lab 4, see how you're doing with that. hopefully everybody had made it through lab 3 all right, so lab 4 shouldn't be too bad because things should already be built and ready for you. It's just some tweaking of different things. And as I said, lab 5 will actually get to work on some hardware, so you get to experience new frustrations.